Let us discuss about partial blockage. So in my chip there is one block. Inside that there is one specified area I am mentioning. This is a partial blockage area. So if I wanted this here, if I can mention it, this partial blockage area is 50%. So 50% of these cells, 50% of this area is placed with cells. So other 50% is going to remain as it is. So I can mention how much percentage I need to place the cell area. The remaining it will be going to left as it is. So I can with this we can reduce the congestion. If congestion is more happened at any point of time, then we can reduce with this technique. Keyboard margin is nothing but a soft blockage. Nothing it can be moved from one place to other. Nothing difference between. Issues due to bad floor plan, congestion near the macro pins, corners. Like congestion will be happening, like due to congestion. So macros we need to place this very perfectly, such a way that shouldn't be causing any timing violations, not any power issues, not any timing issues, or not any congestion issues. So while doing power also, I'll add a point here. While doing power planning, so uh, while doing power planning in the top level, right? So my stripe is at the top level. So if you are if my macro is placed at some M3 or M4, so if my macro is placed here, so through vias, let us take M10 through vias. If you are taking it to the M4, even though if you are taking that power is not sufficient to this macro which is placed in the M4. So what should I do? So then I'll be creating a stripes in these macros in M5 or M6, so that uh, I'll be giving a different power pin, and I'll be giving this to this macros. So this will be easy for doing the power planning. So we like the power, it won't be power hungry, right? So macros are more power hungry. So if you are doing this thing, the load on the mesh is going to be decreased, right? Obviously, that is what we need to understand. If you got my point, am I right? And next, power plan. As we know that thing, power plan is we are creating the pre-routing. So nothing but routing routing in the topmost layer. Through vias we are taking to the down layers. M1 layer is nothing but, and I'll show you the power mesh. These are the formulas we are going to discuss it later. So if you see here, uh, we are doing through ring. This is a ring around the core area. So inside one is the die area. Here this is the die area. The inside square is there, right? That is the die area, and the around outside one is the core area. Die is the outside one, sorry. Die is the outside one, and core area is the inside one. Core area is which we place the standard cells. So a ring we are created around these things, around in the space between the die and core area. After that, through stripes we are taking to the uh, to inside this power to inside our core area. After the core area, then through vias we are taking to the lower layers, M1, M2, M3. So while doing this thing, the vias will be helping us to moving the power from one layer to other layer. So we need to take care that our power shouldn't be the power is uniform all over the things, all over my layers. It won't be uniform as the via size is going to decrease and the resistance is going to increase. Obviously there will be a voltage reduction. That is why we need to take care. And this is the formulas. So total dynamic power divided by core voltage is the dynamic core current, and pad width, total dynamic core current is the total. This will be in the UPF file, number of sites plus max current source per site. Core width, total dynamic core current, number of sites, Jmax of the Jmax is nothing but the current density of the metal layer for ring and current source per site. Power power stripe spacing, core width minus and this spacing is based on the offset. This is not a compulsory one. I will tell you one trick. So initially we need to mention this grid offset. Okay, after that we need to specify the spacing between that. If it is 5 micrometers, then we need to tell the spacing. Obviously with 5 micrometers it is going to place it here. After that the spacing between these two is 5 micrometers, and this is with these two is 10 micrometers. According to that spacing these types are going to place. Okay, and ring stripes, rails are nothing but the routing layers on the yeah, first metal layer M1. We say it as these blue lines are there, right? These blue lines inside on the bottom layer, those are the S route. And the power vias are nothing but the from M10 to M1 there are some vias going to be placed, right? So those are vias. Trunks is to connect uh, core pad will be placing on the outside from pad to ring. This is called trunk. This is the full chip. These are trunks, if you see, right? These are the trunk, and this is the power to macro. And we save this def, floor plan def. At every point of time we are getting that def. Okay, physical only cells, well tap cells, end cap cells, decap cells, all these cells. Well tap cells are for latch up purpose, and end cap cells is for well proximity effect. What is well proximity effect? If you well proximity effect is like if I had one MOSFET at end of the channel, right? I will be having the poly here active and all those things, no? So oh sorry, uh, so poly. So whenever the charge is while doing the fabrication, right, if it is the end of my block, so there will be cutting process happening, there will be charge accumulation, and this will be damaging the poly here. So what we need to do is to we place a dummy cell which doesn't have a functionality. So end caps doesn't have any functionality. So even though if it is damaged also, I'll be very happy that that won't create any damage to my functionality of the chip. Good. Cell padding is nothing but giving space between the cells. To this is for congestion purpose we are adding spare cells. Even after routing also, if I wanted to change any functionality of the circuit, I can change that. I can just take the metal layers, BOE layers, I mean top layers, and connect where we are needed. We just place the cell. According to that, we just change the metal interconnect layer connections only. Okay. And pre-placement goals, in at every point of time, my goal is to reduce timing, congestion, power, area. These are my main goals. Okay. Optimization before placement. Okay, this thing, if the in synthesis we used to had wire load models, right? So we need to remove those wire load models, zero RC extraction, like so inbuilt some wire load models are being added, so we need to remove those things. So for better understanding, if you are removing that, right, so we can do the actual placement, and we can do the actual routing, and we can do the we'll be getting the actual wire load model. Then that is good, right? That is good. This is an approximate one. It may or it may not be. Isolation cell insertion. Isolation cells are nothing but uh, that whenever we have multi voltage, right? I'll explain this thing. If this is always on block, this is always on block, on block, on block. So this is switching block, off block. Whenever this is off, right, this need to be always on. But how do I on? So based on some switching given here, right? So we will be placing OR gate here. Even if it is off, if I am giving one signal, this block is going to turn on. That is the thing will be going on. So this cell is an isolation cell. So the placement, in placement, standard cells placement we used to do, and the placement main objective is to reduce the total wire length, and routability, performance. And performance is nothing but timing performance. Wire length, that wire length is nothing but based on the wire length only, we are calculating the manufacturing cost. If the wire length is reduces, the manufacturing cost obviously will be reduced, though the power is reducing and heat dissipation is also reduced. If based on these things only, right, based on the placement, if placement is good, obviously the CTS will be good, obviously the routing also will be good. Timing checks at slow corners. So here, after already we had built the MMC corners, right, we used to check at the slow corners. Timing check only we are doing, like timing checks, in that only we are doing setup timing only. We can do the hold check also, but that will show that since we don't have the actual clock, we can't able to, we can do, but that is not realistic. It is approximately the tool will be giving. There are two types of placement: timing driven placement, congestion driven placement. In timing driven placement, we used to based on the congestion, timing, power it is going to do. Like if the large critical paths are there, that uh, that that path's timing should be reduced. So why we need to do critical path analysis? So if the longest path is there, let us consider this is the longest path, I o output. So if this is the longest path, so the data is taking more time to travel from here to here. Obviously the performance of my chip is going to degrade it. The frequency I need to uh, like the frequency is obviously going to reduce, right? Obviously time period is more, 1 by t. time period is more, frequency is less. I need to compensate my frequency. There are three types of placement in this thing. Global placement, this is a rough approximate placement, this is not an exact placement. There will be happening of 25 to 26 iteration in total placement. So approximately to this global placement will take 5 to 6 iterations to get whether not 5 to 6, it may be more than that, depends upon the instance count, how which will be the good based on the iterations. If it is taking more iterations only, we can, this tool can judge whether this is good one or bad one. And the detail placement, the cells are going to be placed in the legalized manner. So if you see, right, there will be no any overlaps in this. There are so many overlaps are happen, there are no overlaps will be happen with other cells. Placement legalization, like in this thing, placed macros are legally oriented with standard cells. This in this there may be some overlapping with macros. Since we don't have macros here, we just neglect that. And in place optimization, scan chain reordering. Let us discuss this thing. Like scan chain reordering, after placement, there the cube, if 1 2 3 4, so 1 2 3 4 5 6, so from here to here it will be happening. So 2 to 3 here, 3 to 4 here, 4 to 5, 5 to 6. So the routing is irregular. So after scan chain, right, so what it is doing was 1 so how it is doing was 1 2 3 4 5 6. So we are reordering the scan chain in a such a manner that if we give the input here, we'll be getting the output here. So so this much clumsy it is not there. So actually we are reducing the delay or congestion, routing congestion. Here the routing congestion is more, whereas here it is very less. That is the scan chain reordering. After that, we used to place tie cells. Why we used to place was, we can't able to connect gate directly to the my VDD supply or any voltage input signal. So through these tie cells only we connect to our gates. So to protect the gate from higher voltages or any glitches we are getting, anything we are getting, right, those the thing. Global route is nothing but based on this global route only we are telling whether this placement is good or not. So we need to discuss whether um, global route is good. uh, Total wire length, we are approximating the total wire length based on the global route. So pre-CTS optimization is nothing but cell sizing, VT swapping, cloning, buffering, logical restructuring, pin swapping, resizing. If you see it here, right, so uh, EA, this has 0.035. After resizing, we are increasing the size. As the increasing the size, delay decreases. Cloning, the breaking the fan outs, I'm creating a duplicate cell. So EAB, here I have only one cell. In buffering is nothing but breaking the fan out and putting the buffer, so it is taking more area, right? In cloning it is taking, whereas in buffering, so I'm trying to reduce my area. So here it is like redesigning based on the arrival times. If A is coming at 4, right, so I can place it here, a late signal. B is coming at 3, I'll be placing it here. CD, it is coming early, so I am placing it this point of time. So A is coming late, that is why I'm putting it is taking less instances. It is taking somewhat middle, it is taking earlyly, this is late. We need to compensate all these things, right? That is the main thing. Decomposition, if why you wish to decompose the cells, if more number of pins are there, if congestion is happening at any point of time, then we used to decompose the cells. Swapping of pins, uh, as we swap the pins here, right? So these are the swapping of pins. So based on the timing only, if it is taking more time, right, obviously it is, we need to swap the pins. C it is taking lately, we are giving it here. A and B are coming early, that is why pre-CTS optimization. And coming to that, these things, HFNS is nothing but mm, uh, the reset signal and clear signal. We need to create a tree type of model, buffering those things. So not a exactly a tree model. um, these things has high fan outs, right? We need to do a some buffer tree such a way that it shouldn't create any violations. That is what shielding and NDR. Shielding is nothing but to avoid crosstalk and all these things. These things we are going to do in CTS, not now, where we are going to discuss it later.